Bismillahirrahmanirrahim. This is the first video from chapter number 4 about combinational logic, and in this we'll learn about adders and subtractors. So what is a combinational circuit? A combinational circuit consists of logic gates whose outputs at any time are determined directly from the inputs. So let's see this diagram. For example, the moment we change these inputs, the output is changed. So this is a combinational circuit. Now in contrast, there is another circuit. Similarly here, the moment you change any of the outputs, the output will change. In contrast, there is another circuit called sequential circuit. Now, sequential circuit employs memory elements in addition to logic gates. So, in addition to logic gates, it also has memory elements, and the outputs are function of the input and the state of the memory element. So, it is not only dependent on the input. For example, if this is the input, the output is not directly dependent on the input, rather it also depends on the memory element, whatever is stored in here, so that is added with the input and then we get the output. For example, this is second. Now this is the part of the combinational circuit. With that there are two flip-flops that have been added, so the output, it depends on not only the input from here, but it also depends on the output of the flip-flops. So this is called sequential circuit. Now we'll be studying here combinational circuit in this chapter. And first of the circuits are adders. And generally, I'm sure you will have an idea. When we add 0 and 0, the answer is 0. When we add a 0 bit and 1, the answer will be 1. When we add 1 and 0, the answer will be 1. But when we add 1 and 1, the answer will be 0 because we cannot have 3. So the answer will be 0 here, but there will be a carry here. So this is a special case you have to keep in mind. When adding 1 and 1, the answer is 0 and we have a carry. And similarly, if we add 3, then actually we are adding 1 and 1, we're getting 0. And then with that we add another 1, then we get 1 here. And from here, the adding 1 and 1, we had got a carry, so we'll write it here. So this is how binary addition takes place. And first we'll discuss about half adders. Combinational circuit that performs the addition of 2 bits is called the half adder. So these 2 bits can be added by half adder, but for the 3 bits we got to have a full adder. Okay, so what are the inputs? X and Y, 2 inputs, and the possible combination is 0, 0, 0, 1, 1, 0, and 1, 1. And now, as we have seen from here, when we add 0 and 0, we get 0. When we add 0 and 1, this is the sum, S for sum, and this is for carry. So when add 1 and 0, we get 1 and no carry. But when we are adding 1 and 1, we get sum as 0 and there is a carry, just like this. Sum 0 and we have a carry. So sum 0 and we have a carry. So this is the truth table for half adder. And now let's see how we can implement this. So from here directly, you know how to write the equation. Like for sum, wherever there is 1, we'll consider that value only. So here it is 1. So what is the input? X is 0, that means we'll write it is X dash, and Y is 1, so we'll write it 1. So X dash 1 Then there is another one at the sum. So we'll OR it with the positive sign, means OR, and this is when the input X is 1 and Y is 0. So that means it's X, Y dash. So X, Y dash. So this is the expression for the sum term. And now let's see the carry term. The carry is only 1 when both X and Y is 1. So X and Y is equal to C. So this is how we write the sum of product expression. And now to implement, these are AND gates, X dash Y, that means actually X dash dot Y, and dot is for multiplication, or we'll do that with the adder. So if we have this input, first of all this one, let's say X dash input and Y input, then the output of the adder is X dash Y, and this is going to the OR gate. So this is for OR gate. So we have implemented this part. The second part is X Y dash. So again we feed X from here and we feed Y dash from here. The output of the adder is X Y dash. This is also coming into the OR gate, and so the output of the OR gate will be this or plus sign, the other one. So X Y dash or X dash Y. So this is how we implement the sum function. And for carry function it will be simple adder. So carry is X into Y. So X input, Y input, and through an adder we get X into Y. So this is carry out. So this circuit will represent a half adder. Now, if you have learned XOR gate, I'm sure you will remember that XOR gate has the property that whenever one of the inputs are different, so like here one is 0, the other is 1, here first one is 1 and the other is 0, so outputs are different, and then this can be implemented by an XOR gate. So this function, you see here also X dash and this is Y, that means 0 and 1, and here it is 1 and 0. So we can represent this by an XOR gate. So XOR gate has output X Y dash plus X dash Y, or we can also write it as X, and this is the symbol for XOR Y. And we are feeding X and Y to the XOR gate. And similarly, for the carry, we use an AND gate and we get the input X and Y from here. And so this is the final answer. So I hope you have understood how to implement half-adder circuit. And this is symbolically we can represent, instead of drawing this whole thing, we can just represent it like this. Two inputs A and B and two outputs carry and sum. Now let's talk of the full adder. Now the full adder will add 3 binary bits, so just like here. So we'll have 3 inputs, and I am sure by now you have learned how to fill in these columns. So we have all the 8 possibilities, 2 raised to the power 3, so 8 possibilities we have written. And now to find this answer, we have to do the addition of all 3. So 0, 0, 0 added becomes 0, 0, 0, 1 will give you 1, 0, 1, 0 will give you 1. Now here there are 2 ones added, so 2 ones means 1 carry, so 1 carry and the sum is 0. And similarly here is 1, here 2 values, so again we get a carry and 0, 2 ones, so again we get a carry and 0, and 3 ones we get 1 and 1 as we had shown here. So this is the truth table for full adder. And now we can write their values in terms of the variables. So for sum here it is 1, 1, 1 and 1, so we'll have 4 values. And for this you can see 0 means x dash, 0 means y dash, and this is z. So x dash, y dash, z. Similarly, you can write all the 4 values from this table. Now we come to the carry. Now carry has 1 here and 1, 1, 1 here. So for this, you can see from here it is x dash, y, z. So we have written x dash, y, z. And similarly, you can write the other 3 values. And now we need to formalize this. So all are added with an plus sign, or that is OR sign. So for sum we can write S is equal to all these OR together, and similarly for carry all these OR together. So this is the formal equation. And now we'll take help of a K-map to simplify, because this may not be the simplified form. So it is better that we use K-map. So I hope you have learned how to draw a K-map. So we have 3 variables, so we'll write it x and y, z, 0, 1, 0, 0, 0, 1, 1, 0 and 1, 1. This is tricky. You have to remember that 0, 0, 0, 1, and then you go to the last one, 1, 0, and then come back for 1, 1. Okay. And now let's plot the sum. For sum we have 0, 0, 1, first one. So we go to this here, from here we get 0 and 0, 1. So we put a 1 here. Similarly, 0, 1, 0, 0, 1, 0 here, and this is 1, 0, 0. So this one is 1, 0, 0, and finally 1, 1, 1. So 1, 1 and 1. So these are the 4 ones we have put in the K-map. Since we cannot further simplify these, therefore we'll write the answer just like this. But now let's see whether we can simplify the carry function. Same way we input the values of the carry functions. So we have a 1 at 0, 1, 1. So 0 and 1, 1. So we put a 1 here. And similarly we put these other 3 ones. And now you can see that you can combine these two. You can combine these two. And you can combine these two. So, and now you can write the equations of these two combinations. From here, if you look, we have x. So we write x. And from here, what is common is z. So we write z. So xz. And then you can write this two. Y and z common. So we write y and z. And then you can write for these two. So x common from this side and y from here, so it is xy. So this is a simplified form. So the carry function has been simplified. Instead of 4 gates, we are using 3 gates, and that too here the gates were 3 variable gates. Here we just using 2 variable gates. So that is the benefit of using K-map for final design. And now for the sum function, 3 variables, 3 variables, 3 variables. So we have 3 AND gates with all these variables written here, and then they are ORed with a 4 input OR gate. So this is the sum function, and same way we can implement the carry function with 2 AND gates, 2 variable AND gates, and they are ORed with a 3 input OR gate. So this is the implementation of full adder. And if you have to write it symbolically, we just write like this. We say full adder, 3 inputs A, B and carry, and the output is sum and carry out. Now let's quickly discuss the half-subtractor. The concept here is that we just subtract from x, y. So this column, which is D column, is the difference or subtraction. And there is another column for raising a flag that you have borrowed 1. So this is for the borrowed. And sometimes you come across a term called minuend and subtrahend. So if you keep this in mind, that the first one, from where we are subtracting, from which we are subtracting, is called minuend, and the item which is subtracted is called the subtrahend, and obviously you get the difference. And from here you can directly write the equation. For D, you can see these two are 1, so we can see from here it is 0, 1, that means x dash y, or from here you can see xy dash, so xy dash. And for the other one, we have just 1 here, so it is x dash y, so borrow is at x dash y. Then we talk of full subtractor. Now the full subtractor, we have to subtract y from x, and then whatever is the result, you subtract z from that. So like here, first of all you subtract y from x. So let's say in the first case 0, 0, so subtracting we get 0, and since this is 0, so the answer also, if you subtract this 0 or z from 0, then the answer will be 0, and there has been no borrow, so the borrow will also be 0. Now next is this one. From here, if we are subtracting y from 0, we get 0, but when we subtract 1 from 0, that is z, we are subtracting from this, we cannot subtract unless we borrow. So we have to borrow. So first of all we raise this flag to be 1. So we have borrowed 1, which has become 2 here. Just like when we borrow in the decimal, we borrow 1 in place of a 0, then it becomes 10. Similarly, here it has become now 2. So 2 minus 1, the answer will be 1. And let's see one more. Third one, here, this one. Now we are borrowing from here because y cannot be subtracted from 0. So straight away we need to borrow. We raise this flag to be 1. And so this will be 2. 2 minus 1 is 1. Now from 1 we can subtract 0. The answer will be 0. So this is how we proceed for the full subtractor. So this is our answer D, difference, and this is for B, borrow flag. And now if you follow this table, we have 1, 2, 3 and 4 ones. So this is for D. Again we just plotted. There is nothing common, so the answer will be just the OR values of all 4 inputs. And now let's see with the borrowed terms. The borrowed terms again we have common here and here and here. So we get a simplified version of the borrowed function. And finally, one simple example. Question number 4.1. Design a combinational circuit with 3 inputs and 1 output. The output is equal to logic 1 when the binary values of the input is less than 3, and the output is logic 0 otherwise. So let's see how does it implement in terms of a truth table. So this is the truth table. Now we have to find their equivalent values, although he is saying binary values, but to me it should have been the decimal equivalent anyway. So let's see, this is the value or the decimal equivalent value. So this is equal to 0, this is 1, 2, 3, 4, 5, 6, and 7. So what it is saying, that the output is equal to logic 1 when the binary values of the input is less than 3. So less than 3 means up to this point, the output should be 1. And for the remaining, it should be 0. So let's plot the output. So this is the output function. So for these three, we have written 1, and for remaining, we have written 0. And now we can design the take help of a K-map. So you see that we have plotted these three in the K-map, and now we'll try to simplify. So you can see these two could be paired, and this one could be paired, and so our equation will be as shown here: x dash y dash plus x dash z dash, and we can implement with the help of a very simple circuit, 2 AND gates and 1 OR gate, and these are the inputs from here. So I hope this gives you an understanding about the adders and subtractor circuits of the combinational logic. Thank you.